Have you ever checked the reviews before buying something online? If you see that more than 50% of people gave it 5 stars, you're likely to buy it. That's statistics in action. Statistics isn't just about math problems, it's how we make decisions every day. From budgeting your family expenses to predicting if a project will succeed. But before we can make those big decisions, we have to turn a mess of numbers into a clear story. Today on STEMBridge, we're going to learn how to organize raw data into powerful tables and graphs. From chaos to clarity, a visual guide to transforming raw data into insight. We know that every great story starts with a messy first draft. Here we have data in its raw form. It looks like a jumble of numbers, but it holds valuable information. It's nearly impossible to see any patterns or draw conclusions from data in its raw form. What stories are these numbers trying to tell? The first step. To begin making sense of the chaos, which is from raw data, we need to arrange the data into groups or classes. This process will turn an unmanageable list into a structured summary, which we call grouped data. Here we have an example of ungrouped data or raw data. It is the data which has not been arranged in a systematic order, while grouped data is a tabular arrangement of data in which various items are arranged or distributed into classes, and the number of items falling in each class is stated. As in this example, we have two columns. The first is the marks obtained, and the second is the number of students. Here, the marks obtained is our class interval, while the number of students is our frequency. Now, what is our blueprint for clarity? It will be the frequency distribution table. This table will be our primary tool for organizing our data. It will neatly categorize our values into specific intervals and count how many fall into each one. We will use it to tame our lamb dataset. Class intervals. They are the groups or ranges we sort the data into. Frequency is the number of data points that fall within a specific class interval or the number of repetitions. The anatomy of a frequency table. So we have the scores, which we call the class intervals. They have the class limits, the smallest or the lower limit, and the largest, which is the upper limit in a class. For example, in the first column, in the first class, 1 is our lower limit while 10 is our upper limit. In the second class, 11 is our lower limit while 20 is our upper limit. Here, class mark, it is the midpoint of a class and it's denoted by X. In order to calculate class mark or the midpoint, you add the lower limit with the upper limit and divide that by 2. For example, in the first class, I have 1 to 10. So this is my scores or class intervals. If I add 1 with 10, that's 11, and 11 divided by 2 is 5.5. So 5.5 is my class mark. Now, what are size of class intervals? If you look at the first class, which is the scores, the lower limit, which is 1, and in the second class, the lower limit, which is 11. You will notice that 11 subtracted from 1 is 10. Then 21 subtracted from 11 is 10. 31 subtracted from 21 is 10. So this will be the size of our class interval. Or simply, it is the difference between the upper and lower class boundaries. But before talking about class boundaries, we need to know what they are. If you look at the first class, which is the scores or the class intervals, you will see that we have the lower limit and the upper limit. If you subtract 0.5 from the lower limit, you will get the lower class boundary, which is 0.5. But if you add 0.5 with the upper limit, which is 10, you will get the upper boundary, which is 10.5. In conclusion, they are the true dividing lines between classes created to handle continuous data, and they are found by adding or subtracting half the difference between consecutive class limits. Structuring our LAMP data, we need to plan our table. Before we can tally our data, we need to decide on the structure of our table. This involves three key decisions. The first is dividing on the number of classes. The second is to find the range, which is the smallest value and the largest value. And the third is to find our value of h, which is the class interval size. So, firstly, depending on the number of classes, a number between 5 and 15 is generally good. So we can choose the value of n, our number of classes, as 5. And we need to find the range. We need to identify the smallest, which is xs, and largest xl values. Suppose xl is 176 and xs is 125. And in order to find the value of h, which is our class interval size, you will simply subtract your larger value with your smaller value and divide that with the number of classes, which we have in this case 5. So you have 10.2. Rounding 10.2, we can round this to a convenient number like 11. So that will be our class interval size. Now taming the numbers one by one. Firstly, what are tally marks? Tally sticks are the ancient tools used for recording numerical data. Marco Polo noted the use of tally sticks in regions like China, Yunnan. Now, with our class intervals defined, we can go through the raw data and mark a tally for each value in its corresponding group. For example, the masses in pounds, that will be our class interval. So we have the first class from 125 to 135, the second as 136 to 146, the third as 147 to 157, all the way to 169 to 179. Now we are going to write their frequencies. This means that how many people had their masses in pounds from the range of 125 to 135. Suppose we have 8. So when we have 8 people that have their masses in pounds from 125 to 135, we can accordingly make tally marks for them. We are going to write a complete set of tally marks. A complete set consists of 5. So we can write 1, 2, 3, 4 tally sticks and then draw a diagonal above it. That will be 5. And then we already have 5 tally marks, so we can just write 3 vertical tally sticks. So that will be our frequency in tally marks. Same as for the second class, the frequency is 13. So we are going to make a set of 5. 1, 2, 3, 4, they will be our vertical tally sticks. But then we are going to draw the fifth line, which will be diagonal. Then this is our first set. So the second set, it will also consist of 5 tally sticks. That adds up to 10. And the last, that will only consist of 3. Why? Because we have 13 frequencies. 5 and 5 make up 10. So the last 3 will be added with 10 to make up 13. Now what is the first glimpse of clarity? Our process is complete. The raw jumbled list of 40 numbers that we had was transformed into a simple, elegant table that reveals the underlying distribution of our data at a glance. Now, seeing our story, we need to know the introduction to histograms. It becomes very easy to get a quick idea of our distribution when we use a graph to represent our dataset. Because as we know, a table is good, but a picture is often better. A histogram brings our frequency distribution to life, allowing us to see the shape and spread of the data instantly. And we know that a histogram represents data by adjacent rectangles having their bases along a horizontal axis. So the vertical axis, which is y, that will be our frequency, while our horizontal axis, which is x, that will be our class boundaries. And the heights of the rectangles are proportional to the class frequencies. Building our data skyline. A histogram is constructed by plotting class boundaries on the x-axis and frequencies on the y-axis. Each bar will represent a class and its height shows how many data points are in it. Here we have a histogram which shows the height in centimeters, which is of 44 students in a secondary school. The height of this bar, which is of a rectangle, it is 9. It corresponds to our frequency of the 136 to 144th centimeter class. Here in the x-axis, we have our class boundaries ranging from 129.5 all the way to 179.5. And our frequency is the number of students from 0 to 12. The story of our labs visualized. We are applying this technique to our case study. Our distribution becomes clear. We can immediately see that the most common mass for lambs is in the 136 to 146 pound range. The shape of this data is now visible. Now we can also trace our trend with a frequency polygon. It is another way to represent our same data. But instead of bars, it uses live segments to connect points plotted at the class marks, also known as the midpoints, for each class interval. A frequency polygon basically is a many-sided closed figure, and it is used to show a frequency distribution. How will it work? Firstly, we will find the midpoint for each class interval, which is h, and then we can plot the frequency against the class mark, and we will join our points with the line segments. Now, connecting the dots of our data, if you see in the first graph, we have made an histogram and we have plotted the frequencies at the midpoint of each class. This frequency polygon gives us a clear line of sight into our data's shape and trend. Now, there is another advanced technique which is handling unequal class intervals. Let's assume that our class intervals aren't of the same size. A standard histogram can be misleading and we want to maintain accuracy, so we must ensure that the area of each rectangle is proportional to the frequency, not just its height. So we can use frequency density. When class intervals, suppose they are unequal, we will plot frequency density on the y-axis instead of just frequency. So what is frequency density? It is basically our frequency divided by our class width. The journey from raw numbers to actionable insight. We now have a systematic process to take any raw data set and transform it into a clear, insightful visual story. We had some raw data which was ungrouped. We made some structure of that and we learned how to visualize that by using histograms or frequency polygons. To conclude this lecture, I'll give you some questions which you need to solve and then you can email me to find out the correct answer. The first MCQ: when data is organized into a table showing classes and the number of items falling into each class, then what is this arrangement called? Is it frequency polygon, raw data, group data, or cumulative frequency? In the second MCQ, for a class interval defined as 21 to 30 in a frequency distribution, what are the corresponding class boundaries? Is it 21.5 to 30.5 or 20.5 to 30.5, 20 to 31 or 21 to 30? Moving on to the third MCQ, what is the class mark or the midpoint for the class interval 136 to 146? Is it 141 or 136 or 10 or 146? Which graphical method uses adjacent rectangles to represent the frequency distribution of continuous data? Is that graphical method histogram, discrete frequency graph, tally bar chart, or frequency polygon? To construct a frequency polygon, line segments are used to join the midpoints of the tops of the bars in a histogram. What are these midpoints on the x-axis called? Frequencies, class boundaries, class marks, or class limits? If the frequencies for the first four classes in a distribution are 8, 14, 12, and 6, then what is the cumulative frequency of the third class? When creating a histogram with unequal class intervals, the height of each rectangle must be adjusted. What is this adjusted height representing frequency per unit of class interval called class mark, frequency density, relative frequency, or adjusted width. Given a data set with a smallest value of 125 and a largest value of 176, what is the approximate size of the class interval if you want to create 5 classes? 60.2, 51, 10.2, or 11? What is the primary purpose of using class boundaries instead of class limits when drawing a histogram? To ensure there are no gaps between the rectangles, to center the data more effectively, to simplify the calculation of frequencies, to make the y-axis scale more accurate. Moving on to the last MCQ, how is a frequency polygon graph typically closed so it starts and ends on the horizontal axis? The graph is left open and does not touch the horizontal axis. By dropping vertical lines from the first and last points to the x-axis, by connecting the first point to the origin, or by adding points for hypothetical classes with zero frequency at both ends. I hope you liked my video. Don't forget to like and subscribe for more ways to simplify this complex. I'll see you in the next one.